Okay, so in the last lecture we derived the Tknn formula, which relates the Hall conductivity of a band insulator to a topological quantum number, which is the Chern number of all the filled bands. But that was rather specific, so we discussed only a band insulator where we assumed that there's no interactions between electrons. We assumed that the motion of every electron is independent of all the other electrons. And moreover, we've assumed perfect translational symmetry. So we assumed that there's no disorder in the system. And of course, real solids have both interactions and disorder. So to really understand why the Hall conductivity is quantized, we need to treat both of these effects. Okay, so what we're going to do in this video is actually derive a much stronger result, namely that the Hall conductivity can be quantized in a gapped system even in the presence of arbitrary disorder and arbitrary interactions. Okay, so this is really what we're gonna prove, that if we have a many-body system of many electrons, finite density of electrons, and the system is gapped, and moreover, we'll assume that there is a unique ground state of a system with periodic boundary conditions. Okay, so if we have, say, if we place our system in a torus such that there's no boundary, the Hamiltonian has only a unique ground state. There's no ground state degeneracy. Then we'll show with very little assumptions that the Hall conductivity is actually equal to an integer times e squared over h. Okay, the quantum of conductance, and this integer valued constant nu would depend, as we'll see, on a Chern number, which depends on the many-body wave function. So the convenient setup to study the Hall conductivity is a system with periodic boundary conditions, which is equivalent to saying that the system is placed on a torus. So here's our system. Let's consider a finite system. We'll take it to be large at the end. So our system is Lx by Ly in size. And the system is characterized by a many-body wave function of n electrons. Okay, so this is a many-body wave function that depends on the positions of all the electrons. Now, since our system has periodic boundary conditions, we can define the boundary conditions as a relation between the phase of the wave function at some position and when we translate one electron by either Lx or Ly. So we can define a twist angle. Okay, that's a very convenient theoretical tool to define twisted boundary conditions. So the wave function, when we take one of the coordinates of the electrons and shift it, say, by Lx in the x direction, is related to the unshifted wave function by this twist phase theta x. This is going to be like a probe that we'll use to both drive the system to represent the electric field and also to probe the current which is resulting from that. Okay, and in the same way, we define another twist angle theta y, which is the angle that results when we shift any of the n electrons by Ly in the y direction. Okay, now we've written here what happens to the wave function when we shift the coordinate of the first electron. Of course, because this is a wave function of electrons, it has to be anti-symmetric. So this actually specifies what happens when we shift any of the coordinates of any of the electrons. Here's our system. So we can imagine the system with periodic boundary conditions as living on a torus. And if you think about what the meaning of these two angles, theta x and theta y, are, these can be actually thought in physical terms, as in terms of fluxes that are threading our torus. Okay, so here's our system placed on a torus, and there's two equivalent fluxes, magnetic fluxes, phi x and phi y, that are threading through the two holes of this torus. So what is the angle theta x? This is like an Aronov-Bohm phase that an electron would pick up if it goes around the torus, because then it went around a flux line phi x. Okay, so we can easily relate the fluxes to the two phases theta x and theta y. Okay, so h bar over e, h over e is phi naught. That's the flux quantum. Okay, so now we can start seeing why this sort of setup is useful. We can use these two fluxes, phi x and phi y, as control knobs. Okay, so what we do is we imagine that they can both depend on time. And if we change one of these fluxes as a function of time, by Faraday's law, that's equivalent to applying an electric field. So we want to probe our system by applying an electric field. And for instance, if we change phi y as a function of time, the time derivative of phi y divided by Ly would be related to the electric field going in the y direction, so wrapping around this hole, and that can be related to the time derivative of this phase theta y. Okay, and what we'd like to do is to apply this electric field in the y direction, and we want to calculate the Hall conductivity, which means that this electric field will generate a current going in the x direction, and we can derive that current also by using our probe flux in the other direction. So you can easily convince yourself that the current density Jx is related to the derivative of the Hamiltonian, the many-body Hamiltonian of the system, with respect to phi x. Okay, so where does this result come from? You can easily derive it by recalling that the current density Jx at position r is equal to minus the functional derivative of the Hamiltonian with respect to the vector potential Ax at the same position r. Okay, and this is the current density at a certain position. If you assume that Ax is uniform, you'll get the average over the current density over the entire system, and this would be the current density at any point. Okay, so this is our setup. What we're going to do is take our Hamiltonian, which depends on our two phases, theta x and theta y, make theta y time dependent to give us the electric field Ey, and then what we want to calculate is the current in the transverse direction. So there's going to be a current in the x direction, and that we're going to express in terms of the derivative of the Hamiltonian with respect to the other phase, theta x. Okay, now it turns out that it's more convenient, rather than calculating this particular quantity, to calculate the averaged current over all the possible values of theta x. Okay, so instead of calculating this, it would turn out to be more convenient to calculate this average current. Okay, so Jx average, that's the average over the current density Jx over theta x from 0 to 2 pi, and over time from 0 to capital T, where capital T is simply the time it takes for theta y to grow by 2 pi. Okay, now why do we do this? You'll see that in a moment, but first of all, physically, just to gain intuition, okay, the averaging over time is not expected to do very much, because after all, we're going to choose our theta as a function of time to represent a constant in time electric field. So the electric field in the y direction is constant. Therefore, we expect also the current density to be constant as a function of time. So we're actually averaging over a constant. Moreover, in the limit where the system is very large, we don't expect any bulk property, and this current is actually a bulk property, it's uniform in the entire system, to depend on the boundary condition that is specified by this phase theta x. Okay, so in fact, in the thermodynamic limit, this is going to be an average over a constant. So this is really just a calculational tool. Well, more on that later on. Okay, but this is the quantity we're actually going to calculate. Okay, so here's our average current over both time and theta x. And let's simplify that a little bit. So this current contains this expectation value in the wave function psi of theta x and t of the theta x derivative of the Hamiltonian. And that's integrated over theta x from 0 to 2 pi. Okay, so that we can rewrite in this form. So we take out the theta x derivative. So it's the theta x derivative of h times psi, overlap with psi, and then we need to subtract the theta x derivative of the many-body wave function itself, and then h sandwiched between psi and that. Okay, so so far we've done nothing here, but now we can use the time-dependent Schrödinger equation that this psi of t satisfies. So as usual, okay, so I h bar dt of psi is equal to h times psi. Okay, and we can insert this both for h times psi and bra h psi times h. Okay, and after a few steps, you get to this formula. So the h has disappeared. It's in the time derivative. It's simply the h bar times the integral over theta x of the overlap between d psi d theta x with d psi dt plus complex conjugate. Okay, and this you can write as the imaginary part of this overlap of two derivatives of the wave function. This is starting to look like the Berry curvature, and this is actually our aim. We want to show that the current can be expressed, and the current and therefore the whole conductivity can be expressed in terms of the Berry curvature of the many-body wave function. Okay, so how do we relate this more directly to a Berry curvature? What we want to do is to replace the time derivative with a theta y derivative. We think about the many-body wave function is depending on two parameters, theta x and theta y, and we can express the whole conductivity in terms of the Berry curvature of the wave function as a function of these two parameters. So here's our current again, with this imaginary part of the overlap of two derivatives. Now, because of the fact that our electric field is very small, that means that theta y, whose derivative is equal to the electric field, is changing very, very slowly as a function of time. So that means that we can use the adiabatic theorem to express the time dependence of our wave function. So psi of theta x and t is actually equal to psi of theta x and theta y of t. Okay, so at any given moment, the time-dependent wave function is very close simply to the instantaneous eigenstate of the Hamiltonian at the same theta x and theta y, up to a phase. And as we know, as usual, for the adiabatic theorem, what this phase e to the I phi is, that's a sum of the dynamical phase and the Berry phase. But that's actually not going to matter for our purpose. Okay, so we substitute this time-dependent wave function back into the expression for the current, and we get the whole conductivity. So the whole conductivity sigma xy is simply the ratio between jx and ey. Okay, and here it is. So we've replaced the time derivative and the time integral by a theta y derivative and a theta y integral. Okay, so this is our expression for the whole conductivity. And remarkably, you see here that the whole conductivity can actually be written as e squared over h times this expression, which is nothing but the Chern number of our theta x and theta y dependent many-body wave function. Okay, so we have a wave function psi, which depends on two parameters, theta x and theta y. Both of these parameters are periodic. They go from 0 to 2 pi. So whenever we have a wave function like that, which depends on two parameters which are periodic, or more generally, we have a wave function that's defined on a compact surface, we can define a Chern number. And this is nothing but that Chern number, okay, which we discussed several times already in this course in different contexts. Here, the interesting thing is that the Chern number is defined not in terms of a single particle wave function, but in terms of a many-body wave function. But other than that, it's the same. Okay, so this proves in particular that the whole conductivity is actually quantized. It's equal to e squared over h times nu, which is a Chern number, and therefore that Chern number is integer valued. Okay, and it's a topological invariant. What we've done is derived a formula for the whole conductivity of a many-body gapped system with arbitrary interactions and arbitrary disorder. What about a non-interacting case of a band insulator that we've discussed in the previous video? Well, as you might expect, this case is just a special case of the many-body case we are discussing now. Okay, so let's just demonstrate that quickly. So here's our band insulator. We have some number of block bands, and all the bands up to the chemical potential mu are filled, and all the other bands are empty. So the many-body wave function from which we can derive the whole conductivity is written like this. So we simply create all the electrons in the filled bands and leave the empty bands unoccupied. Here 0 is the vacuum state. It's the state with no electrons in it. Okay, and now what we saw is that one can express the whole conductivity of any many electron system in terms of a Chern number of this many-body wave function as a function of the two twist angles, theta x and theta y, of the system on a torus. So how does this many-body wave function actually depend on theta x and theta y? Well, recall that this is just a non-interacting system. So if we have our system with periodic boundary conditions with a twist, what the twist angles theta x and theta y would do is simply shift the quantization condition of the allowed momenta on the torus. Okay, so in particular, we know that if we have untwisted boundary conditions, the allowed periodic boundary conditions, the allowed momenta are 2 pi times an integer over L, the size of the system, either in the x or the y direction. And if we have twisted boundary conditions, that shifts the allowed values of kx and ky by either theta x over Lx or theta y over Ly. Okay, so this is how the many-body wave function would depend on the twist angles through its allowed momenta. And now we can simply insert this many-body wave function into our formula for the Chern number that determines the whole conductivity. So you can easily check by using this wave function that the Chern number can be expressed in this form, where u and k is the periodic part of the wave function of the block state of band n and momentum k. Okay, so this simply reduces, it's a few lines to check, this simply reduces to the expression we had for the whole conductivity in the case of a band insulator. Okay, and on the way, this is a useful exercise to do to fill in the few steps missing here. Okay, and one thing you'll note if you do this is how in the thermodynamic limit, where the system is very large, the value of the whole conductivity doesn't actually depend on theta x and theta y. Okay, so it's actually the same, independent of theta x and theta y. So in the thermodynamic limit, this Berry curvature is actually independent of the two angles. Okay, so just before we conclude, there's one more interesting comment. Okay, so what about the fractional quantum Hall effect? So we seem to have proven very generally that any many-body system with arbitrary interactions and disorder has a whole conductivity which is e squared over h times an integer. But we saw earlier in the course that there exists also quantum many-body states that have a fractional Hall conductivity. For instance, there's a fractional quantum Hall state whose Hall conductivity is 1/3 times e squared over h. And that's also constant, it's independent of detail, but it's a fraction. So how is that consistent with the result we've just derived? So it turns out that the assumption that we've made, which is not valid in the case of the fractional quantum Hall state, is the assumption that there's a unique ground state of the many-body system for any theta x and theta y, and this ground state never crosses another state as we vary these twist angles. Okay, so in the fractional quantum Hall state, as we've actually discussed before, the many-body ground state of the system is nearly degenerate when we have periodic boundary conditions. And as we increase the system size, these nearly degenerate states are going to become closer and closer in energy. Let's take an example. So this is what the spectrum, the many-body spectrum of a Laughlin state, fractional quantum Hall state, with a filling fraction of 1/3 might look like schematically. Okay, so there's a spectrum which is a function of both of these twist angles, theta x and theta y. And we're drawing here a cut through this spectrum as a function of one of the parameters, say theta x. So for a filling fraction of 1/3, what we'll find is that the system, the many-body system on a torus, has 3 nearly degenerate ground states, which are separated from the rest of the spectrum by a gap. Okay, so the splitting between these 3 states would scale like e to the minus the linear size of the system divided by a correlation length, which in the case of the fractional quantum Hall state, this correlation length would scale like the magnetic length. Okay, so as we increase the system size, this splitting between the 3 states would become tiny. Okay, so these 3 states are not really distinct. They're all part of essentially the ground state manifold, and the gap to the rest of the spectrum remains order 1. Okay, it doesn't collapse to 0 as a function of the system size. Okay, so because we have these 3 states that are so close in energy and might even cross each other as a function of theta x and theta y, we cannot actually compute the Chern number of each one of these states separately. We can, however, compute the Chern number of all 3 states together as a function of theta x and theta y. Okay, so these are like 3 bands that we treat together, and we compute just a single many-body Chern number of all 3 bands together, And if we do that, we'll get the result that the Chern number of these three states is actually equal to 1. Okay, so if you like averaging over all three states, we get that the whole connectivity is E squared over H. It's quantized, as we derived. It has to be. But because this whole connectivity has to be divided into 3, because each one of these states is essentially identical, has the same whole connectivity, its whole connectivity would actually be 1/3. It would be a fraction of E squared over H. Okay, so just to summarize, what we've done in this video was to derive the whole connectivity of a many-body gapped disordered system. We've done that assuming that the ground state is unique. And what we've shown is that using a trick, placing the system on a torus and changing the twist angles of the boundary conditions, we can derive quite generally that the whole connectivity is equal to an integer, which is the Chern number of the many-body wave function, times E squared over H. And we've shown how that gets modified in the case of the fractional quantum Hall effect, where the ground state is actually not unique. So just to summarize this video, here we discussed the whole connectivity of a many-body gapped system. And we assumed that on the torus we have a unique ground state separated from the rest of the spectrum by a finite gap. And we could relate the whole connectivity to a Chern number of the many-body wave function as a function of the two twist angles theta x and theta y on the torus. This actually shows that the whole connectivity is quantized even in the presence of arbitrary many-body interactions and disorder, as long as the many-body gap remains finite. Finally, we discuss how this gets modified in the case of the fractional quantum Hall effect, in which the ground state is actually not unique on the torus. There's a finite many-body ground state degeneracy. Okay, thank you.